In this video, I'm going to be going through some examples of related rates applications involving circles and spheres. So let's start off with an example problem. Pebble is dropped into a calm pond, and it's causing ripples in the form of concentric circles. You could imagine something like this. The radius of the outer ripple is increasing at a constant rate of 1 foot per second. So the radius from the center where the pebble dropped out to the outermost ripple would be considered the radius. And so that length is changing, it's increasing at a rate of 1 foot per second. So when the radius is 4 feet, at what rate is the total area of the disturbed water changing? So we're trying to find the area at a exact moment in time for all of these ripples. And at that exact moment, the radius is 4 feet. So let's think about what we have. What information are we given? What equations might we want to involve? Since we're trying to find the area of a circle, then we might need the area formula. So pi r squared is the area of a circle. We know the radius at this moment is 4, so when r is 4, we're going to solve for the change in the area with respect to time. So we're going to find dA dt when r is 4, and we're given one more thing. We're given the rate at which the radius is changing, so we could call that dr dt and set that equal to 1. So we know we're involving the area of a circle. We're going to derive that with respect to time. If I derive a with respect to time, I get dA dt. Pi is just a constant number. We're not going to derive that. So we'll just take the derivative of r squared with respect to time. That's 2r times dr dt. So now we can substitute what we know. We know that r is 4. We know that dr dt is 1. And we're solving for dA dt, which is set up already. So we just got to simplify 2 times 4 times pi, which is 8 pi. Or we could round that to 3 decimal places and say that the area is growing or increasing because we have a positive rate of change at a rate of approximately 25.133 square feet every second at the exact moment when the radius is 4 feet across. Let's try one more example here. This time we're going to talk about a sphere. In this example, air is being pumped into a balloon at a given rate, at a rate of 4.5 cubic feet per minute. And we want to find the rate of change of the radius at the exact moment when the radius is 2 feet. So if the balloon is changing size, that means that the volume is changing size. So we're going to include the volume formula. We're given a rate. We're given the rate at which the volume is changing or increasing because it's a positive rate of change. So we're given dV dt, or the rate at which the volume is changing with respect to time. And we want to solve for the rate at which the radius is changing. So we're going to solve for dr dt at the moment when r is 2. So let's derive the volume formula and see what we get. 4/3 and pi are both constants. So I don't need to take the derivative of those. I just take the derivative of r cubed with respect to time. That's 3r squared times dr dt. And we know what r is. At this exact moment, it's 2. And we know what the change in the volume is. We know what dV dt is at this exact moment. So substitute 4.5 there. And then we're solving for dr dt. So simplify the right side. Multiplying by 3 and dividing by 3 is just going to cancel those. So we got 2 squared, which is 4, times 4, which is 16 times pi. So if I divide both sides by 16 pi, I can solve for dr dt. So that's approximately 0.884 rounding to 3 decimal places. So what does that mean? That means that the radius, that's our change in radius, is increasing or growing at a rate of approximately 0.884 feet per minute at the exact moment when the radius is 2 feet. So a couple examples involving circles and spheres. talking about area and radius of a circle or volume and radius of a sphere.